Hi, my name is Richard Monge. I am a graduate student at the City University of New York Graduate Center. I work at the City College of New York campus with Professor Carlos Meriles' group. And today I will present work that my colleagues and I have been doing on the suppression of noise in a scanning single spin probe near a superconductor. So the single spin probe that we use is the nitrogen-vacancy center in diamond. This defect in diamond is composed of a substitution of nitrogen adjacent to a vacancy. And this gives rise to special localized electronic states that allow for the initialization and optical readout of its spin state. If one were to apply a microwave field from a nearby microwave antenna, at resonance we see dips in the fluorescence. In addition, if one were to apply a magnetic field, we observe the Zeeman effect. So via the shifts of the optically detected magnetic resonance lines, or ODMR, we can obtain quantitatively the magnetic field. Since this is an atom-size defect, it is also an atom-size sensor capable of nanoscale imaging as well. One of the basic forms of sensing with the NV center is DC sensing. So work in the past decade has been focused on integrating the NV center into scanning probe microscopy through the use of these special AFM probes. These AFM probes have been precisely fabricated to host a single or several NV center at the apex. In addition, one of the advantages of this NV AFM probe is one can use this to approach the sample very, very close and achieve nanoscale resolved magnetic imaging. Again, through the shifts of the ODMR lines, one can map out the magnetic field of any sample. For example, in here, they imaged the magnetic field from a vortex on top of a superconductor when the superconductor is in the mixed state. And this was back in 2016 by Maletinsky's group. Another form of sensing is AC sensing. So now the NV center spin can also be manipulated. So one of the many advantages of the NV center is its ability to implement time-resolved protocols. And one can engineer these protocols or pulse sequences to filter out the specific frequencies and obtain more information about the source of noise responsible for the decoherence of the NV center. From the coherence curves, one can also obtain spectral properties of that source of noise. So in Jacobi's group at Harvard back in 2016, they used these same probes to monitor the surface spins of this adjacent diamond sample. As you can see, as they approach the NV center close to the diamond, they observe a much lower coherence lifetime. In here, they are basically imaging the magnetic field fluctuations. And from here, one can obtain the spectral properties of these surface spins from such decoherence imaging. So along these lines, we implement these protocols to monitor the source of noise from these NV AFM probes when we approach a superconductor. So our setup is composed of a patch of high temperature superconductor, and we perform magnetometry with the aforementioned NV center probes. And we have an RF wire nearby to excite the NV center. So if we perform magnetometry on top of a corner patch, we expect the Meissner effect. When a superconductor is in the superconducting state, it will exclude any magnetic field. So in here, we observe the Meissner effect. We see that in here, at top of the superconductor, there is much less of a magnitude of magnetic field. In addition, something we observed is that there is an effect the superconductor has on the microwave field strength that we use to drive the NV center from the RF wire. In here, suggesting that the superconductor has a high frequency response. So then this led us to investigate a bit further by implementing much more complicated sequences such as a Han echo and a CPMG to investigate the frequency response of the superconductor. So we perform the following experiment. We take these NV, this single NV, and we approach it off and on top of the superconductor, and we perform a T2 protocol. These revivals and collapses are due to a nearby coupled carbon-13, and the oscillations are determined by the carbon-13 Larmor frequency in the applied magnetic field. But I want to bring to your attention only the envelope of these curves. So this envelope actually gives us the coherence lifetime, or the T2 of that NV center. So away from the superconductor, at spot B, we see 28 microseconds of T2. On top of the superconductor, however, we see an enhancement of the T2. We see a 43 microseconds of T2. To further confirm this effect, we fix our probe on spot A and vary the distance away and close to the superconductor. As you can see, close to the superconductor, we still get a 43 microsecond of T2. Away from the superconductor, we see this enhancement effect being much less, 29 microseconds of T2. And we could take this a step further and perform it at several steps away from the superconductor, and we observe a trend. Clearly, there is an effect the superconductor has on the T2 of this probe. So, as I mentioned before, one can implement and engineer these sequences to probe specific frequencies. And in order for us to see if there were any anomalies in terms of frequencies that we are probing, we perform the CPMG sequence. For CPMG 8, we still observe the same effect. So we see that on top of the superconductor, there's an enhancement of the T2 as compared to off the superconductor. By varying the number of pi pulses, we also still observe the same effect, where on top of the superconductor, there's much higher T2, as you can see, regardless of the number of pi pulses that we use. We could take this a step further and perform a T2 weighted line scan. But as I mentioned before, both the microwave field strength and the magnitude of the magnetic field are changing as a function of position. So then, in order for us to perform a T2 base scan, we need to apply corrections, both to keep unaltered all the duration of these pulses in the sequence, and also to keep exciting on resonance the NV center. And once we apply these corrections, we still observe the same effect. On the left side is off the superconductor, on the right side is on top of the superconductor. You can clearly see that on top of the superconductor there's an enhancement. So at the interface, however, we see a decrease in the T2, and this we have yet to further simulate. Nonetheless, we observe the same effect. So we observed the Mize effect, and that was expected. One thing, however, we didn't expect is the enhancement of the T2. So somehow, the noise that's responsible for the decoherence of the NV center is somehow being suppressed, and we have to consider two sources of noises. One is electric fields from surface charge fluctuations, and the second one is magnetic field fluctuations from surface paramagnetic centers. So the magnetic field fluctuations, based on our calculations, cannot be shielded to the extent that we see, which is at the micron range. However, if we consider electric field, from our calculations, the electric fields can actually be shielded to that extent. And these calculations we're putting together in preparation for submission in the manuscript. So this is further supported by previous work by Daniel Rugar at IBM that suggested, and they showed that the main contributor for the decoherence of these near surface nitrogen vacancy centers is due to electric field fluctuations. All of this work opens up a prospect to increase the bandwidth and the sensitivity of the NV center, because the sensitivity is tied to the T2. In addition, we are working on possibly extracting some information of the superconductor from the spectral density that we get from the coherence curves, such as we expect maybe to get the frequency pinning of the vortices when the superconductor is at the mixed state. So I would like to give thanks to everybody involved in this project, in the Meriles group, and Nicholas Proscia, who was previously in our group, but he's currently at the Naval Research Lab. He put together the software that made the magnetometry possible, and Kinami, who provided the diamond probes. Thank you very much.